Back from lunch, everyone. So the first talk of the afternoon will be by Meghal Gupta on error correction for message streams.
Okay, yeah, as Jelani said, I'm going to talk to you about error correction for message streams. My name is Meghal, and this is based on joint work with Rachel Zhang. Okay, so I guess let's start by defining the problem. So, like in a standard, in the standard setting of communication, Alice has a message X that she wants to send to Bob, and then Bob wants to output like X, and that means that he's received the message. So in the streaming analog of communication, Alice is still going to send a message X to Bob, but now instead of outputting all of X, because like he doesn't have space to store all of X, he's just going to output some function f of X. And f of X is some function that like can be computed, and the final output is in significantly less space than X. We'll say that throughout the talk that X is in 0, 1 to the n. And for example, one thing that Bob could be computing is f could correspond to some arbitrary y in 0, 1 to the n, and f of x could be y dot x. So like f could be some arbitrary linear function. So in this case, for example, Bob would be able to compute f, which is equal to y dot x, in log space, because he has to store like the index I that he's currently on, as well as like a running sum. And I'm considering all of these in like f2. Does that make sense? Okay, so what is like the standard setting of error correction? So in the standard setting of error correction, Alice wants to send a message to Bob such that he is still able to output X in face of like a small constant fraction, like delta fraction of errors. So delta fraction So now instead of sending X directly, Alice is going to have to send an encoding, which we call ECC of X. So does that make sense? So like the main question that we're going to be discussing in this talk is what happens, can you do the same thing? Can you error correct in the streaming setting? So what is the analog of this question in the streaming setting? So we want Alice to send something to Bob such that Bob is still able to output y dot x. Right now, we'll just consider linear functions, but at the end of the talk, we'll go back a little bit to general functions. So Alice wants to send some encoding to Bob, such that he's still able to output y dot x, and he's still able to compute this value in polylog space. So if Alice just sent like Bob a standard error correction or standard error correcting code, then the problem is Bob would need to first decode ECC of x and then compute y dot x. So that isn't actually low space because Bob actually needs to store the entirety of ECC in part of his protocol, right? So the question that we're going to be discussing is whether there actually is like an analog of this concept for the streaming model, because it's not at all obvious that. I guess this sort of highlights the reason why the question is inherently different in the streaming model than in the standard model, because in the standard model, you can actually just send like a global error correcting code and then decode the entire thing at once, but here you can't actually use that solution. So can you do this question? Yeah?
So the errors, are they adversarial? They can cluster in the beginning, or? Yeah,
so the errors here can be adversarial. The adversary will know what X is beforehand, as well as know what process Alice is using to encode X, and based on this can decide to to concentrate all the corruptions at the beginning if they want.
Bob knows Y without paying in space?
Bob's algorithm is allowed to depend on Y, so yeah, I guess in some sense he knows Y without paying any space. So does the model make sense? Okay, so the main theorem that we're going to discuss in this talk is the following. The main thing we're going to do is we're going to answer this question in the affirmative. We're going to say that this encoding does actually exist. The main theorem is that there exists an encoding that goes from messages of length n to encodings of length approximately n squared. This n squared is not necessarily tight, but this encoding uses length n squared. Like there might be better encodings, and that's going to be an open question later. Such that Bob can let's say Bob can compute such that Bob can compute y dot x in polylog n space given 1/4 minus epsilon error, adversarial error with high probability. All right, does the theorem statement make sense? Okay. Yeah, so I guess now we're gonna, the main, I guess, yeah?
So 1/4 minus epsilon is the value of delta from beforehand?
Yeah, that's the value of delta from beforehand. I guess I won't be too careful about chasing this exact constant though in the outline I'm gonna give right now. So I guess as a brief outline of the rest of the talk, we're gonna prove this. The proof is not actually that complicated, but I guess this talk is not actually that long either. And then I'm gonna spend a little bit of time talking about open problems because like this model is like a new model. It's just like what can you do for error correction in the streaming model that you could do in the original model, and what can't you do that you could do in the standard model. So I'm going to discuss a few open questions, but really like anything you can do in this standard model is probably fair game, and like those are all reasonable open questions to work on. Yeah?
Do you construct this encoding, or do you just show that it exists?
We construct the encoding. Okay. Does that seem reasonable? I don't know. Can I move on? Okay. Cool. Okay, so let's start like looking for this encoding. So earlier we talked about like why sending just a standard error correcting code doesn't work, right? Because it's sort of like too global. Like you actually need to know all of ECC of X at once, right? So like the next natural thing to try, I guess, is an LDC. The reason that an LDC is natural is because it has like more of like you don't have, I guess you don't have to do like the same like storing of the entire thing at once, storing of the entire like error correcting code at once in order to be able to do some sort of decoding. So the first thing we're going to try is have Alice just send LDC of X to Bob. Let's define what an LDC is. So we're going to be using polylog query. Yeah?
What's an LDC?
A locally decodable code. So we're going to define it. Okay, so an LDC is a locally decodable code. We're going to be using a polylog query LDCs. So let's say what that means. So an LDC is an encoding that maps strings of length n to strings of length slightly longer than n. I think in this case, they're going to be like O tilde of n, but it doesn't like really matter. And importantly, they're going to have the following properties. Bob can recover a single bit xi with polylog n queries. What that means is he has a randomized process for choosing like polylog n locations of the encoded message and just querying those locations, and then he can recover xi. The reason that this is important is because it also means that if he receives LDC in a streaming manner, he only needs polylog n bits of space in order to recover xi, because there are only polylog n like indices that he actually needs to ever read. So that's the reason that we're going to be trying to use LDCs at the base of our construction, because they're a way to decode. They're sort of a way to do decoding while only using a small number of using only a small amount of space. So the problem though is that like Bob can only recover a single bit this way. Importantly, this is resilient to error. So resilient to 1/4 minus EPS error. Yeah, so like, I guess the thing that we would hope for, I guess if we actually wanted to go back and compute y.x, the problem is we would need to recover all of x1 through xn using the same LDC. That's not actually okay, because then you would have to go back to needing theta of n space, right? But like, you can recover a single bit. You can only recover a single bit using this method. That's why this is not actually okay. So let's try another attempt that doesn't really work. Let's have Alice send LD like n copies of a locally decodable code, LDC of x. And then in the first one, Bob is going to recover x1. The second one, he's going to recover x2. And the last one, he's going to recover xn. So this would work. So if every single copy of LDC were only corrupted a little bit, like every single copy were corrupted less than a fourth, then Bob could use these values to keep track of a running sum and compute y.x, right? But that doesn't actually work because the adversary can choose to corrupt this entire message. And then x1 will be decoded incorrectly, right? And then at the end, Bob will, in fact, output potentially an incorrect answer. So the main thing we're going to try to do with our construction is try to get around this issue so that Bob will actually be able to compute x, so that Bob will actually be able to recover each of these xi's on average correctly, like all of the xi's on average correctly, instead of like only being able to recover like half of them correctly. But we're going to still use copies of LDC as our base construction. Okay, so to do this, we're going to define like, let's look at what's going on in terms of a tree structure. Like the final construction is going to be recursive in some sense. So the function that Bob is computing, f, which is like y.x, can be broken into two parts. We're going to write it as f1 of x plus f2 of x, where f1 is like the first half of y, and f2 is the second half of y. So like this is like y1. So I guess you can think of this as like y1 x1 dot y n over 2 x n over 2, and f2 of x is like the second half, right? Whoops. Does that make sense? Yeah, so in a tree structure, what's going on here is Bob is computing f1 and f2. And here he's like splitting this again, computing f11, f12, dot, dot, dot. And then at the base level, he's computing xi dot yi for some values of, I, right? If you're trying to look at like what he's doing over here. So the issue is that the adversary can take a single one of these leaves and destroy it, right? So what we're going to do instead is try to make the average. So the problem is that the adversary is like, corrupting f1 and not f2 here, right? So what we're going to try to do is instead make it so that the adversary doesn't know when f1 and when f2 are being computed, so he can't actually target errors on only one of them. So what we're going to do is we're going to add like a bunch more like leaves here. And we're going to have the adversary, we're going to have Bob compute f1 and f2 both a bunch of times. So Bob is going to have like a lot of leaves in this tree. Let's say like, we'll specify the exact amount later, but let's say like log n leaves. And then he's going to compute f1 half the time and f2 half the time in some randomized way that the adversary has no idea of. So the adversary cannot concentrate errors on only f1 or only f2. And then the adversary is going to go ahead and then Bob is going to go ahead and recurse this process. So now he's going to compute f11 a bunch of times, f12 a bunch of times, or I guess these are 2s, and so on. And then basically like we're going to have the same base nodes of xi.yi. But now the point is like, you don't actually need all of the base nodes to be correct. You just need that on average they're correct. Like let's look at like the top layer again. So in this layer, the way that Bob is going to determine the value of f1 at the end is he's just going to take the majority of all of these outputs, and that's going to be his value of f1. So it wasn't necessary that all of the outputs were correct, but just that the majority was correct. Makes sense? Yeah, so I guess if you do the computation out, it turns out that the number of children you need is polylog n in order to guarantee that as you go down through the layers, that actually all of these, that actually F1 will be correct and F2 will be correct. It turns out the number of leaves you need per layer is polylog n, which would give a total amount of, which would mean that the total number of nodes at the base were polylog n to the power of log n. Because like the total size of the tree would be this quantity. So I guess I promised you something slightly different. I promised you that the number of nodes at the base would be theta of n, because like each LDC is also like approximately length n. So then that would give you the n squared from like the theorem statement. So this is like slightly different from this quantity. The way to fix that is actually pretty simple. Right now we have f being split into two parts, f1 and f2. Instead, we could split it into polylog n parts. And in essence, that would mean that the number of layers goes, instead of being log n, the number of layers is log base polylog of n. And if you're careful about your constants, you would be able to get theta n for the number of nodes. Yeah?
He's like, how come he couldn't have just, for every bit, tried to decode it like log n times, but at random times, and then every bit with good probability could have been corrupted to the time.
So are you suggesting sort of like,
The tree, I got confused.
I guess that sort of comes into play with the memory. So the point is like when Bob is computing F2 over here, he actually like doesn't need to store any of the memory from the base recursion of F1, right? And that's where his memory advantage is coming in.
I got it,
Yeah. So I guess I should have been clear about like why this is actually polylog n memory, but it's just because every time he's computing F2, he doesn't need to store any of the nodes of F1. So at any point you sort of are only storing one path on the tree. Okay, does that make sense? Yeah.
What's the output length?
The output length is just a constant because like F2 is just F2 or F1 is just like this quantity here, like y1 x1 dot 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 yn over 2 xn over 2. So the output is just a constant.
You mean the sum.
Oh yeah, it's just the sum. Sorry. Yeah, okay. Yeah, so the output. So I guess the things you're going to need to store are you would need to store every value you've computed of F1 so far, so that you can take the majority at the end. You can do a slight hack to not actually have to do that, but like more or less you're gonna have to do that, and you're having to do the same thing for F2, but that's like not a whole lot of memory. That's like approximately log memory.
So if my function f is not a dot product but a streaming algorithm, I should think of f1 as the intermediate memory state.
Yeah.
I see.
Yeah. So I guess the issue with a general function would be that in order to be able to do these computations out of order, you actually need like F2 to not depend on F1.
Oh yeah.
So I guess in order for this protocol exactly as stated to work, you would in fact need that property, which is why I wanted to only go over for dot product, because yeah, otherwise you run into that issue.
So you cannot do arbitrary.
This way you cannot do arbitrary cryptographic digest or something. So it has to be linear operator.
Okay, so actually the theorem statement that we prove in the paper is a little bit stronger. We actually are able to get arbitrary functions. The only caveat for the arbitrary functions is that they actually have to be deterministic. And the caveat is that instead of getting n squared, you end up getting n to the fourth. So this construction here has the issue that like you need to know the value of F1 before F2, but you can do something where you just take your like best guess for F1 and you can prove that like it works, but it takes longer to converge. So that's why you need n to the fourth instead of n squared. Is that like sort of clear? I don't really want to go into the details of that. Sorry, okay, I think that wasn't clear then. Okay, I guess let me state like a different theorem. There's a different theorem in the paper which says that you can compute any function f of x in s dot polylog n space, where f of x in the noiseless setting would take s space to compute. And instead of n squared over here, you would have an n to the fourth over here. But I'm not going to go over the proof of that right now. Okay, so I think that's like most of the math I wanted to cover. So I wanted to like say some of the open questions, and you guys should work on them because I think they're interesting questions. Okay, so the first one is what communication blowup is needed. So in the theorem we said earlier, and the construction we described, the amount of communication that Alice needs to send is n squared, right? Like it's quadratic in the length of the original message x. So the question is, can you do this in linear? I don't know if a lower bound that shows that you can't. And like maybe you actually can. So yeah, so the first question is, can you do that? Like even just for the dot product case, even in just like the linear function dot product case, can you do n squared and, or sorry, can you do theta of n? And also what's the best you can do in the general case? Can you just get n theta of n for all of them? I don't know, like maybe. Also maybe there's a lower bound against it. So the second one is concerning a different function other than dot product. So I guess the second one is going to be about space blowup. So the general theorem is that for any function s, or for any function that f that used s space, the space of this algorithm will be like s times polylog n. So in the case where s was already pretty big, like s was already log n or polylog n, maybe this isn't that concerning, right? Like polylog n is not that much bigger than n. But in the case where s were like a lot smaller, like you could imagine there are functions where s is log n, then this is actually a pretty big blow up. So in that case, is like the polylog n necessary. So an example of such a function is the following. You have Alice who has an input x, and Bob has I, and he wants to output xi. So if Alice just naively sends over x, then this would take Bob like log space because he would need to like count. He would actually need to like count the. Sorry, he would need to count the indices of the input. But actually, there's a message that Alice can send to Bob so that this process only requires log n space. Alice can send j, xj for all values of j between 1 and n. And then in order to check, and then in order to decide whether to output xj, Bob just needs to check, does I equal j? To output xi, Bob checks, does j equal I? Because, and then if j equals I, then he just outputs the next bit, right? And but j is only length log n, because like the index itself is length log n. So Bob only needs to check if all of the bits of that log n length string are equal to all of the bits of his string. So actually, this process only requires log n bits. And I guess a concrete question about space is, can you find an encoding? So there is a way to send a message x across such that Bob can output xi in log n bits. Is there a way to send x across so that in the face of error, Bob can output xi in log n, in polylog n bits? Yeah, so I guess that's another interesting question. I don't know of a way to do that faster than polylog n because the space of this blowup is polylog n. Yeah?
I don't know, maybe it's just me. I didn't get why this doesn't index have the log bits. Or was it just me that was confused?
Right, okay, so j is some number between 1. There's some reason, okay, sorry. Oh yeah, sorry. So j is some number between 1 and n. So j requires log n bits to store. I think I explained it incorrectly. So you were right to catch me on that. So J requires log n bits. So J is in 0, 1 to the log n. And in order to determine if if two length log n strings are equal, I claim that only log n bits of memory are necessary.
Yeah.
And then because you just keep a counter, you just keep a counter to go through this entire string and through this entire string and check if they're equal. So you're right. I in fact messed up what this exponent was. Yeah. So the question is, can you do this problem can you preserve the log n-ness of the memory of this problem? And I'm sure there's like tons more interesting problems because like I don't know. I guess you can ask a lot of questions that you ask about regular error correcting codes in the case of like streaming in the case of like message streams. So yeah, I guess that's my talk. You guys should try the problems. I don't know. I think they're good. Yeah.
I think this is a really basic question. I just don't know. It's like if you were just in a locally decodable string.
I have a feeling is going to like point out, I know very little about error correcting codes, but if you're just in the locally decodable code case, the space complexity is what? Like I'm assuming it's better than log n because otherwise your question 2 would be pretty hard, right? Like let's say I just wanted to find one bit, like, yeah. Is the space, yeah.
I mean, I think for locally decodable codes, you probably need log memory because I guess even if you were able to get like short locally decodable codes, you would still need to be able to count indices into the, like as the way we know how to do locally decodable codes, you need to like count bits in, you need to actually be able to count the length of the stream. Like the important thing about like trying to break the log n barrier is you can't actually count into the stream anymore.
So it would have to be like even something that goes beyond a locally decodable code.
Yeah, it would have to use something different than locally decodable codes or somehow get around like actually counting into the locally decodable code. I guess you could try to get around counting into the locally decodable
Yeah, I guess
code.
you have to you mean like you have to decide where to access it and that takes log n bits already.
Yeah, exactly.
Yeah, I understand. Okay, thanks.
Yeah, so like maybe it's just not possible, but like, I don't know. I guess then you could try to prove it's not possible. Yeah.
So can you tell me again what this S is? It's the space needed to compute f of x?
Yeah, space to compute f of x without error. So like in the setting, I guess in the setting where you just had Alice sending a message x to Bob, and then how fast can he output f of x without error? Or like how much space does it take him to output f of x without error? I guess even in this setting, Alice is allowed to potentially encode her message into like some different message m of x. But like the point is there's no error. So S is just the space needed in order for Bob to compute f of x in the setting without error.
So could you take me through why in this like J or like this IXI case, it would be log instead of log?
Right. Yeah. So I guess this is maybe because I didn't really define this well earlier, but even in the case without error, Alice is allowed to encode her message because we're allowing her to encode it in the like error case. So why not in this case? So instead of sending x directly, Alice is going to send j, xj for all values of j ranging from 1 through n. And then Bob is going to try to figure out what xi is, given those as his message bits instead of like x1 through xn as his message bits.
Okay, so it's like the sort of amount of information that needs to go over the channel in the noiseless case.
Oh, S is the amount of space Bob is going to take.
Okay.
The amount of memory that Bob has, not the amount of communication.
Wait, so how does this handle with like Bob? Because I still takes like the integer I that Bob has to have still takes log n space, right? So how do we?
Yeah, so I guess Bob's algorithm is going to depend on I, but he's not actually going to store I. He can't store I because it's too much space, right?
Gotcha. Okay.
Yeah. So his algorithm is going to depend on I. I guess you could also think of it as he has read access to I.
Mm-hmm.
Yeah. But the point is like, yeah, it is true that I will not count in his memory.
Okay. Cool. Thank you.
I guess I'm wondering, is there any sort of version of the problem where Alice maybe doesn't see X all at once, but rather gets X herself in some online manner? Maybe you have to weaken the adversary in that case. But is there any model where that might make sense, where she can encode what she sees so far and send it to Bob, and then can run history?
Yeah, I think that's an interesting question. Yeah, I don't know the answer to that one. I think that would be interesting to answer. I guess like in the normal, in the like non-streaming version, there's some like tree codes, right? That sort of do this thing.
Mm.
So I wonder if you can make tree codes like low memory tree codes.
So you erased the theorem, but it seems to me that the parameters of your scheme were very close to parameters of the LDC that you are using. So is there a generic version of the theorem where if you have an LDC with this many errors, this length, you get error correction in message streams with this many errors and this length?
Yeah, so I guess for the linear case, for the case of like linear, yeah, for the case where the function Bob is trying to compute is linear, you need a communication of like theta tilde of n times the length of the LDC. And I think the amount of space you're going to need is like a lot of still a lot of polylogs times like the space of the LDC. And I think it'll be like n cubed and like a lot of polylogs for general functions.
And what about the error? And I guess my question is...
Yeah, so the error is actually the same as the LDC. The error, if the LDC is resilient to like delta error, then you'll get delta minus epsilon.
But does it need to be adversarial? Because it seems here that you're basically randomizing the errors. So if I give you an LDC with, say, better error, but randomized errors. So you assume you have an LDC that can take a quarter of adversarially chosen errors, but actually here you don't care because you're randomizing everything, right? So if I give you an LDC that's good enough with, let's say, half random errors or something, would that also work? Or
I think the thing is the adversary can still target like these base nodes are still going to be LDCs, right? So I think the adversary can still adversarially correct within an LDC. The point of the recursion is that the adversary can't decide which LDCs to corrupt more. The adversary can still say like, I'm going to corrupt all the LDCs, like exactly 1/2, and then do adversarial corruption within the LDC. Maybe there's like some way of like randomizing what LDC you're using, but I feel like that might involve like shared randomness. I guess the point is like, this is only saying that like you can make the adversary not really be able to predict which copies of LDC that are going to be important, but like you can't this isn't actually like making the errors within the LDCs look random.
Any further questions for Meghal? Let's thank the speaker. We have a break until